Acid-base equilibrium, calculating pH and properties of strong acids and bases. In this tutorial, we will be going over how to estimate pH and the temperature dependence of Kw, calculating pH worked example, properties of strong acids, properties of strong bases, worked examples calculating the pH of a strong acid, and finally, a worked example of calculating the pH of a strong base. Estimating pH. Let's look at the pH of 4.72. The number in front of the decimal point is our magnitude. The numbers after the decimal point is our measurement, specifically how many significant figures are involved in this pH. Let's talk about how to estimate pH. Consider the hydrogen ion concentration of 6.24 times 10 to the negative 5 molar. To estimate this pH, we're going to take the absolute value of the negative 5, which is coming from right here, minus 1, which will equal 4. That 4 is our estimated pH. It will go before the decimal place. Now the numbers after the decimal place are something, but we can't really figure out without doing a calculation. Now if we wanted to do a calculation to figure out what these numbers are, we'd need to take the formula pH is equal to the negative log of the hydrogen ion concentration. So we'd take our hydrogen ion concentration right here and plug it into our formula. So pH is equal to the negative log of 6.24 times 10 to the negative 5 molar. And then we'd complete that calculation and find that our pH is 4.20. So the number of significant figures here matches the number of significant figures here in our original concentration of hydrogen ions. Let's do another practice problem. Estimate the pH if the hydrogen ion concentration is 8.0 times 10 to the negative 3 molarity. So to estimate this, we would take the absolute value of the negative 3, and the negative 3 is coming from right here, minus 1, which will give us an answer of 2. So our estimated pH is 2. If we wanted to calculate the pH, we take pH is equal to the negative log of the hydrogen ion concentration. We would substitute in the 8.0 times 10 to the negative 3 value into our formula, and then our calculation would find our pH to be 2.1, which has the same number of significant figures as our original concentration. Temperature dependence of Kw. Let's start out by looking at the autoionization of water, represented as 2 moles of water forming hydronium ions and hydroxide ions. This table shows the relationship between temperature and Kw. The pattern that we can see looking at this table is as temperature increases, our Kw is going to also increase. In this equation, we can represent temperature over on the reactant side. So as temperature increases, the reaction shifts to form products. So temperature favors the endothermic direction. The autoionization of water is endothermic in the forward direction. Regardless of temperature, the hydrogen ion concentration and hydroxide ion concentration are always equal in pure water or neutral solutions. For solutions that are not neutral, find the concentration of hydrogen ions and hydroxide ions by using the formula Kw is equal to hydrogen ion concentration times hydroxide ion concentration. Calculating pH worked example. Calculate the pH of water at 50 degrees Celsius. Let's start out with the formula Kw is equal to the hydrogen ion concentration times hydroxide ion concentration. By looking at the chart on the previous slide or in your notes, the Kw at 50 degrees Celsius is 5.48 times 10 to the negative 14. And that's going to equal our hydrogen ion concentration times hydroxide ion concentration. Because this is Kw in a neutral solution, the concentration of hydrogen ions and the concentration of hydroxide ions are exactly the same. So to figure out pH, we need to calculate the hydrogen ion concentration. So another way of representing this is 5.48 times 10 to the negative 14 equals hydrogen ion concentration squared. To calculate hydrogen ion concentration, we're going to take the square root of 5.48 times 10 to the negative 14. When we take the square root of this number, our hydrogen ion concentration is 2.34 times 10 to the negative 7 molar. Now that we have this hydrogen ion concentration, we can use the formula pH is equal to the negative log of the hydrogen ion concentration to calculate pH. So we'll start off with our formula. We'll plug in our value for our hydrogen ion concentration at this temperature, and our calculated pH is 6.63. Let's do another example. The hydroxide ion concentration of a solution at 60 degrees Celsius is 9.6 times 10 to the negative 11. Calculate the hydronium ion concentration of the solution at this temperature. The pKw is equal to 13.017 at 60 degrees Celsius. So one thing to remember, if the antilog of the negative pH is going to give us the hydrogen ion concentration, so if we take the antilog of negative 13.017, our Kw will be 9.6 times 10 to the negative 14. We can use this Kw to solve for our hydronium ion concentration. So we're going to start with Kw is equal to the hydronium ion concentration times hydroxide ion concentration. We're going to plug in our value for our Kw and our hydroxide ion concentration, which is given in the stimulus. And when we solve for our hydronium ion concentration, we find it to be 0.001 molar, or 1 times 10 to the negative 3 molar. Based on this information, we can make a claim classifying the solution as acidic or basic. So our claim here is that this solution is acidic. Our evidence is that our original hydroxide ion concentration is 9.6 times 10 to the negative 11 molarity, and our calculated hydronium ion concentration is 1 times 10 to the negative 3 molarity. Since the hydroxide ion concentration is less than the hydronium ion concentration, the solution is acidic. Properties of strong acids. Strong acids will ionize completely, leaving no unionized molecules in solution unless the question clearly indicates otherwise. Strong acids are strong electrolytes and exist only as ions. The more easily an acid gives up a proton, the less easily the conjugate base accepts a proton. The stronger the acid, the weaker the conjugate base. In an equation with a strong acid, we will have an arrow represented like this one in the equation to show a non-reversible reaction. The most common strong acids that are necessary to know include hydrochloric acid, hydrobromic acid, hydroiodic acid, perchloric acid, nitric acid, and sulfuric acid. An example of a strong acid like perchloric acid in water shows this single arrow forming hydronium ions and perchlorate ions. So an aqueous solution of HClO4 is assumed to consist entirely of hydronium ions and perchlorate ions. Properties of strong bases. These will also dissociate completely, leaving no undissociated compounds in solution unless the question clearly indicates otherwise. Strong bases are strong electrolytes and exist only as ions in water. We'll also have a single arrow in the equation to show a non-reversible reaction. These will include group 1 metals and heavier group 2 metals. The most common strong bases that are necessary to know include lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. An example of an equation involving a strong base is strontium hydroxide dissociating completely to form strontium ions and hydroxide ions. So an aqueous solution of SrOH2 is assumed to consist entirely of strontium ions and hydroxide ions. Worked example, calculating the pH of a strong acid. Estimate and calculate the pH of a 4.881 times 10 to the negative 3 molarity solution of nitric acid at 25 degrees Celsius. So in the beginning, the concentration of our nitric acid is 4.881 times 10 to the negative 3. Water is not included as it is a liquid, and there is no nitrate ions or hydronium ions present. When this reaction occurs, all of the nitric acid is going to ionize completely to form nitrate ions and hydronium ions. When this acid fully ionizes, the concentration of nitric acid will be 0. The nitrate ion is not going to be considered as we estimate and calculate the pH because the nitrate ion is a spectator ion. And the only thing that we're looking at is the concentration of the hydronium ion. So let's start out by estimating the pH based on this concentration. So we're going to take the absolute value of the negative 3, which we see right here. We're going to subtract 1, so our estimated pH would be 2. If we were to do the calculated pH, we'd use the formula pH is equal to the negative log of the hydrogen ion concentration. We'd substitute in our value, so pH is equal to the negative log of 4.881 times 10 to the negative 3 molarity. And then when we complete this calculation, we find our pH to be 2.311 to the correct number of significant figures. Let's do another worked example examining the dissociation of a strong base. Estimate and calculate the pH of a 3.7 times 10 to the negative 4 molarity solution of barium hydroxide at 25 degrees Celsius. In the beginning, we're going to have a concentration of 3.7 times 10 to the negative 4 molarity for the barium hydroxide, with no barium ions present or hydroxide ions present. As the barium hydroxide dissociates completely, we're going to have equal amounts of barium ions and hydroxide ions, except we need to note that the barium ion to hydroxide ions are in a 1:2 ratio, which is why this is 2 times 3.7 times 10 to the negative 4 molarity. When the barium hydroxide fully dissociates, no barium hydroxide will be left in solution. We're not going to consider the concentration of the barium ions in this problem, as the barium ions are spectators. And our final concentration of hydroxide ions is going to be 7.4 times 10 to the negative 4 molarity. To find the estimated pOH, we're going to take the absolute value of the negative 4, and that negative 4 is coming from right here. We're going to subtract 1, and then our pOH is found to be 3. To figure out the estimated pH, we'll take the formula pH is equal to 14 minus pOH, which we just calculated. We'll substitute in our values, and our estimated pH is equal to 10. To find the calculated pOH, we'll use the formula pOH is equal to the negative log of the hydroxide ion. We will substitute in our hydroxide ion concentration, and then we'll solve for pOH, which is 3.1. Now that we have the pOH, we can calculate the pH. So we'll take the formula pH is equal to 14 minus pOH. We'll substitute in our values of 14 minus 3.1, and our calculated pH is 10.9. So what did you learn? We talked about how to estimate pH and the temperature dependence of Kw, calculating pH worked examples, properties of strong acids, properties of strong bases, calculating the pH of a strong acid, and then calculating the pH of a strong base. Need more help? Feel free to contact me. Have a great day.